You are standing in the cold blue hour before dawn, staring at a patch of sky that looks completely still. The subject is 3I/Atlas, a small, dark comet from another star, quieter than its name sounds. If scientists are reading it correctly, this faint traveler may be carrying a record from a time before our sun was even born, and that changes everything that follows. Stay close and subscribe for clear space stories like this, because the biggest turns in astronomy often begin as tiny moving specks. At first, there is nothing dramatic about it. No fireball, no giant tail filling half the sky, just a weak blur crossing the dark, the kind of thing most people would never notice, and would never guess might hold one of the strangest clues we have ever seen. That is part of what makes this story so unnerving. 3I/Atlas did not arrive like a monster. It arrived like dust on a black window. And yet, piece by piece, telescope by telescope, it started doing something science was not ready for from an interstellar comet. The alarm here is not about danger to Earth. NASA was clear that it never came close enough to threaten us. The real alarm is quieter than that. It is the sound of old ideas shifting, because this little visitor may be telling us that the galaxy has been making icy worlds far longer, and in stranger ways than we thought. Before this becomes about the science, it begins with something simpler. Most people hear the word comet and picture the same thing every time. A dirty snowball from our own solar system, bright for a while, then gone. And even if one comes from another star, the common assumption is that it will still be basically familiar, just rarer and farther from home. That assumption felt safe in the summer of 2025. On July 1st, a NASA-funded Atlas survey telescope in Rio Hurtado, Chile, reported the object to the Minor Planet Center. Later, older images pushed its trail back to June 14th. At the start, 3I/Atlas looked like a fast new visitor, and nothing more exotic than that. Its name sounds louder than the object itself. The 3 means it is the third known interstellar object ever found passing through our solar system. The I stands for interstellar. Atlas is the survey that spotted it, one piece of NASA's skywatching network that scans for moving things night after night, the way a guard walks the same quiet hall again and again. This is one reason comets are easy to underestimate. Most of the time they are introduced to the public as leftovers, frozen scraps, bits of old building material. The language makes them sound passive, like gravel in a cosmic ditch, and once that picture settles in, it is hard to see them as storytellers. But comets are really moving records. They carry ice, dust, and trapped chemicals from the place and time where they formed. Warm them in sunlight, and they begin to leak their history into space. A comet's coma, the cloudy shell around its core, is not just decoration. It is material being released, almost like breath on cold glass. That was already true for comets born around our sun. Scientists had spent decades learning how familiar comets behave. They knew about dust tails and ion tails. They knew that sunlight heats surface ice until gas escapes. They knew that this outgassing can nudge a comet a little, changing its path by a small amount, like a shopping cart pulling to one side. So when 3I/Atlas appeared, the first job was simple: figure out whether it was truly from outside the solar system. NASA later explained that its speed and its path gave the answer. It was on a hyperbolic trajectory, which means it was moving too fast to stay bound to the sun. Trace that path backward, and it did not lead home to our neighborhood at all. Even that fact, amazing as it sounds, can trick the mind. Because once a visitor is labeled interstellar, many people stop there. Rare object, nice headline, keep looking. That is what happened with 1I/Oumuamua in 2017 for many viewers, and even with 2I/Borisov in 2019. They were startling, but they still felt like brief interruptions in a much larger sky. 3I/Atlas seemed ready to play the same role. NASA's facts page said it had an icy nucleus and a coma. Its color, speed, and direction all fit with comet behavior. When it was discovered, it was moving about 221,000 kilometers per hour. At perihelion, its closest point to the sun, that speed rose to about 246,000 kilometers per hour, or roughly 250,000 by ESA's estimate. Fast, yes. Historic, yes. Still, familiar. That was the mood. An interstellar comet, but a comet all the same. Not a rebel object, not a cosmic machine, not a threat. Just a rare traveler following the same old rules under brighter lights. There was more reason to think that. Hubble observations by August 20th, 2025, let astronomers estimate the nucleus at somewhere between about 440 meters and 5.6 kilometers wide. That is a big range, but the point was simple. This was not a planet, not a moon, not some impossible giant. It was small enough to fit the known story of a modest icy body moving through on a one-time pass. Its route also looked calm from a human point of view. It came no closer to Earth than about 270 million kilometers, or 1.8 astronomical units. On December 19, 2025, when it made that closest pass to us, it was still far beyond any real danger. It went closest to Mars on October 3, 2025, at about 29 million kilometers. At the end of October 2025, it passed closest to the Sun at about 1.4 astronomical units. If you stop there, the story almost closes itself. A faraway comet, a high speed, a famous origin, a good science target. And then, after a few months of watching, it would slip back into darkness, carrying its secrets away faster than we could open them. That was the deep assumption under everything. Not that 3I/Atlas was boring, no one thought that. The assumption was smaller and more dangerous. It was that the object would stay blurry in the one way that matters most to science. Interesting enough to watch, but not rich enough to truly read. You can hear that assumption in ordinary language. People call comets dirty snowballs, as if the phrase settles the matter. They imagine a chunk of ice and dust, a tail, a close pass, and then a fade. Even many space fans carry that picture around. Once a comet matches it, the mind relaxes. And 3I/Atlas seemed to reward that relaxation. It had a plume, it had a tail. It followed expectations well enough that NASA said the small changes in its path were compatible with normal outgassing. Everything pointed toward a familiar physical process. This was the cosmic version of hearing a strange accent and realizing the sentence still uses the same grammar. There is a comfort in that. If objects from other stars turn out to behave like ours, then our solar system feels less special and more understandable. The galaxy becomes a place of repeating patterns. A comet is a comet is a comet. Different home address, same basic story. By late 2025, that was the neat picture holding the frame together. A third known interstellar visitor, bright enough to study, safe enough to enjoy, strange only in its passport. Most people, and even plenty of careful followers of space news, were now standing on that picture as if it were solid ground. But that picture is about to change. What we have just taken for granted turns out to be a small part of a much larger story. 3I/Atlas was not just passing through our telescopes, it was beginning to open itself in ways no one could safely assume were possible from an interstellar comet. Leave a comment with the moment your own assumption cracked. That one detail helps this channel see which surprise deserves the next deep dive. Because the next part of this story is not about seeing one more comet. It is about realizing the galaxy just handed us a much older archive than expected. The first real crack appeared when scientists looked for ordinary activity and found something vivid. In early August 2025, ESA said Hubble captured a dust plume coming from the sun-warmed side of the comet. A tail was beginning to show too. The expected result was a dim, moving blur. The actual result looked more like smoke lifting from a hidden campfire far out at sea. That mattered because active comets are easier to study. When ice warms and turns directly into gas, it carries material away from the nucleus into the coma. That gas can be split by light. It can glow in different wavelengths. It can reveal pieces of what the comet is made of, the way steam from a pot tells you there is water inside before you ever lift the lid. Then came late August 2025, and the picture sharpened again. The James Webb Space Telescope looked at the coma and found carbon dioxide, water, carbon monoxide, carbonyl sulphide, and water ice. The expectation had been a broad, vague chemical profile. What scientists found was a surprisingly legible list. It was like opening the pantry of a house on a distant street and recognizing several foods at once. That result cut two ways. On one hand, it made 3I/Atlas feel familiar. Water and carbon-bearing molecules are not weird by comet standards. On the other hand, that familiarity was its own shock. Here was an object formed around another star, drifting for ages between stars, and it was still telling a chemical story our instruments could hear clearly. The closer it came to Mars in early October 2025, the more attention gathered around it. ESA's Planetary Defense Office used telescopes in Hawaii, Chile, and Australia, plus data from the ExoMars Trace Gas Orbiter to refine the path. That is a very modern sentence. It means the solar system is no longer being watched from one porch, it is being watched from many porches at once. Again, the expected version of this pass was frustrating. A comet from another star was going to move through awkward viewing angles. Parts of its trip would be hidden. Earth-based observers would lose time. The sky itself would work like a curtain at exactly the wrong moment. And for a while, that is what happened. Near the end of October, 3 I/Atlas moved behind the Sun from Earth's point of view. Ground observatories and many telescopes in Earth orbit were effectively blinded. The expected result was a gap, a blank page in the timeline, a part of the story where scientists would have to shrug and wait, like readers missing a chapter torn from the middle of a book. But the solar system now contains more eyes than it used to. Europa Clipper, a spacecraft built to study Jupiter's moon Europa, happened to be in the right place. According to a SETI discussion with Dr. Cynthia Phillips of NASA's Jet Propulsion Laboratory, the mission quickly repurposed planned observations. The expectation was silence. The actual result was an unexpected witness stepping out from a different angle in the room. Europa Clipper could not even use its visible light cameras. Those remained covered. Instead, its ultraviolet spectrograph became the hero. From about 1 astronomical unit away, roughly 100 million miles from the comet, it detected hydrogen and oxygen in the coma. That pointed to water ice, like finding 2 wet footprints when you cannot see the bucket that spilled. This did not mean water itself was a shock. Comets often contain water. The surprise was where and how the evidence arrived. At the very moment many observers were blind, a spacecraft built for another mission caught the chemistry anyway. That is the kind of turn science loves, because it feels less like a planned march and more like a door opening from the side. There was another surprise tucked inside those ultraviolet data. Scientists did not see signs of fragmentation or bizarre behavior at closest approach. The expected fear with an unusual visitor is that it may come apart or behave wildly under heat. What they found looked stable. The comparison is almost funny. A stranger walked into the room, and instead of shouting, it spoke in a calm, readable voice. That calm was important. It told researchers that 3 I/Atlas was not only visible, it was coherent. Its activity could be followed. Its structure could be reasoned through. And the geometry mattered too. Europa Clipper was looking from a position that changed how the tail and coma appeared, almost like walking around a statue instead of staring from the front. Soon after that, the comet reached another strange threshold. ESA reported that in late November and early December 2025, the X-ray telescopes XRISM and XMM-Newton detected a diffuse X-ray glow around the nucleus. This made 3 I/Atlas the first interstellar comet observed in X-ray light. That is a sentence worth slowing down for. Not the first comet in X-rays, the first interstellar comet in X-rays. The expected picture of an interstellar visitor was still a fuzzy one, bright in ordinary ways maybe, useful yes, but not something that would step into high-energy light and stay readable. Instead, 3 I/Atlas did exactly that. It was like meeting a traveler from a distant town and then hearing them speak on a radio frequency you did not know they carried. That glow did not mean the comet was dangerous. It meant the environment around it was active enough, and the observations were good enough to reveal interactions invisible to normal sight. The object was no longer just a smudge with a tail. It was becoming a layered event. Dust, gas, ultraviolet signatures, and now X-ray behavior were all entering the same file. By then, more missions were joining the chorus. ESA said the JUICE spacecraft saw a clear tail and structure in the coma, with data arriving in February 2026. Mars missions also contributed. This mattered for a reason bigger than one comet. Scientists were testing a new style of astronomy in real time, using a distributed fleet of spacecraft as mobile observatories. That shift is easy to miss if you focus only on the object, but it changes the meaning of the object. For decades, a rare visitor might pass and leave us with a handful of Earth-based views. Now, a comet can cross the inner solar system and be watched from Earth, from Mars, from deep space spacecraft, and from instruments designed for completely different targets. The sky has become harder for surprises to hide in. Even then, the biggest reveal was still ahead. Early results made 3 I/Atlas look familiar in behavior. That almost hid the deeper shock in its chemistry. The expectation was that if the comet proved readable, it would mostly confirm broad similarities and stop there. What came next suggested a much older and stranger origin story. By January and February 2026, powerful telescopes were turning from simple detection to finer fingerprints. ESO later described observations with the Very Large Telescope that measured isotopic ratios in 3I/Atlas. That phrase sounds technical, but the idea is simple. Isotopes are slightly different versions of the same element, like coins with the same face but different weight. Those ratios matter because they preserve history. They tell scientists about the environment where material formed. Heat matters. Radiation matters. The age and chemistry of the parent star system matter. And according to ESO's July 6, 2026 release, the very first observations of this kind for a comet formed outside our solar system were now possible. The expected result was modest, maybe a few hints, maybe rough similarities to our own comets. What researchers found instead was unusually high carbon and nitrogen isotopic ratios. Aravind Krishnakumar of the University of Liège was named among the scientists explaining that difference. The comparison you can feel is simple. This was no longer reading a label on a bottle, it was reading the handwriting of the place that bottled it. Another study, highlighted by ESO and linked to work led by Martin Courdenay at NASA Goddard Space Flight Center, found a similar carbon pattern and elevated deuterium. Deuterium is heavy hydrogen. It is hydrogen with extra mass. That extra weight becomes a clue because it tends to collect differently under different conditions. Finding more of it is like noticing a recipe used more coarse salt than the version your family always made. And there was more. A team using ALMA, the Great Radio Telescope Array in Chile, measured deuterated water, sometimes called semi-heavy water, in 3I/Atlas. They also found elevated levels compared with solar system comets. The expectation was family resemblance. The actual result looked more like a family resemblance with a face from a much older photo album suddenly shining through. This is where the story widened beyond one object. Cyrielle Opitom and collaborators, cited by ESO, argued that 3I/Atlas likely formed in the outskirts of an old, low-metallicity star system. Low metallicity sounds odd, but it just means a star with fewer heavy elements than younger stars like the Sun. That points to a system born when the universe was less chemically rich. In plain language, 3I/Atlas may have formed around a star much older than ours. Some studies went even further. ESO said the evidence from different teams pointed to 3I/Atlas being more than twice as old as the Sun. Pause on that. Our Sun is about 4.6 billion years old, so this little comet may be carrying ice from a system older than roughly 9 billion years. That is not just old, that is old enough to make our whole solar system feel newly built. And now the earlier surprises click into place. The familiar water signatures from Webb and Europa Clipper did not mean sameness. They meant continuity across the galaxy. Water can show up in planetary systems not just here, but elsewhere too. Yet the unusual isotopes and heavier forms of hydrogen suggest that familiar ingredients can be assembled under very different conditions, in much older neighborhoods of the Milky Way. It is tempting at this point to make the story too neat. So this is the moment to slow down and admit the edges are still rough. Scientists do not fully agree on every detail yet. They are still working through what all of the dust, gas, plasma, and isotope data mean together. Some measurements point clearly toward great age. Some interpretations still need time, comparison, and argument. That uncertainty is not a weakness. It is the strongest part of the story. If all teams agreed too quickly, you should trust it less. Real science gets more careful as the implications grow. And the implications here are large enough to deserve that caution, because they reach far beyond one passing comet and into the history of how worlds formed across the galaxy. Think about what was expected at the start. A rare interstellar comet. Interesting, yes. Probably familiar in broad ways. Probably too brief and too fuzzy to tell us much more than the fact that it came from elsewhere. Now think about what actually happened. It became active enough for Hubble to see a dust plume. Webb read a list of released chemicals. Europa Clipper caught ultraviolet evidence of water-derived species during an observational blind spot. XRISM and XMM-Newton detected the first X-ray glow from an interstellar comet. Then, major telescope studies measured isotope fingerprints that pointed toward an ancient, low-metallicity birthplace. Each step followed the same three-beat rhythm. Scientists expected a glimpse. They found a readable signal. And the surprise kept landing with the same force, like hearing a stranger tell you not just where they are from, but who their grandparents were and what their town smelled like in winter. By the end of this sequence, 3I/Atlas was no longer just another object crossing a chart. It was a message carrier. Not a perfect one, not a complete one, but a real one. A body from another star system had let us read deep clues about age, chemistry, and formation, with a precision few expected from such a brief visit. And here is where this stops being about one comet and begins being about us. If the reveal in this story is right, then the way we think about the galaxy shifts quietly but permanently. The old question was whether other star systems make icy bodies like ours. The new question is how many kinds of icy history the galaxy has been hiding in plain darkness. Share this video with one friend who still thinks comets are just dirty snowballs. Passing it on is the right next step because this is one of those stories that changes how ordinary sky words feel. After this, the word comet sounds bigger. After this, old ice sounds like evidence. What changes first is not the sky, it is the search. 3I/Atlas showed that a fast, distant visitor can become scientifically rich if enough instruments move quickly and if enough teams are willing to improvise. That means the next interstellar object will not simply be watched, it will be hunted, sampled by wavelength, and cross-checked from many positions almost immediately. That shift may sound technical, but it affects what future discoveries become. A decade ago, a rare object might pass with giant gaps in the record. Now, researchers know to treat the whole solar system as an observing platform. Spacecraft built for Jupiter, Mars, or some other target can suddenly become comet watchers if geometry lines up. The lesson is simple. Do not wait for the perfect mission when a good angle already exists. The second change is deeper. 3I/Atlas suggests that icy bodies formed around very old stars can still preserve readable chemistry after drifting between stars for immense spans of time. That means interstellar space is not just a graveyard, it is a storage room. Things can survive there, things can travel there, and sometimes, if we are lucky, they pass close enough for us to hear them speak. This matters for a human reason too. When scientists talk about isotope ratios and deuterated water, they are really asking a family question on a galactic scale. How common are the ingredients that make worlds? How early did those ingredients get organized? How many times has the universe made the cold chemistry that later becomes oceans, atmospheres, and maybe biology? There is a domestic way to feel this. Open a freezer drawer and look at old frost along the back wall. It is not beautiful, it is not dramatic, but it tells you where cold has been sitting, what has leaked, what has lasted, and how long a closed space has been keeping a record. 3I/Atlas is that kind of record, except the freezer is the galaxy. The dates help make the change feel real. June 14, 2025, is where pre-discovery images later found it. July 1, 2025, is when Atlas reported it. August 20th gave Hubble's size estimate. October 3rd brought the Mars flyby at about 29 million kilometers. Late October marked perihelion, with speed near 246,000 kilometers per hour and a distance of about 1.4 astronomical units from the Sun. Then the precision keeps tightening. December 19, 2025, was its closest approach to Earth at roughly 270 million kilometers. Late November and early December 2025 brought the X-ray observations. February 2026 brought JUICE data showing a clear tail and coma structure. July 6, 2026 brought ESO's public release pointing toward an old, low metallicity origin, possibly more than twice the Sun's age. Those numbers do something important. They turn wonder into a timeline. They remind us this was not myth. This was not one blurry picture and a viral caption. This was a chain of measurement, and every new date added a new layer to the same object. That is how a passing mystery becomes part of science instead of part of folklore. Acting on that lesson means changing what scientists build toward next. More rapid coordination, more flexible observing plans, better ways to hand off a target from one telescope to another, and perhaps most of all, more respect for faint objects that seem modest at first glance. 3I/Atlas was small enough to fit inside old assumptions, and rich enough to break them anyway. There are still open questions everywhere you look. Exactly where in that ancient system did it form? What kind of star threw it out? How violent was that ejection? How common are those unusual carbon and nitrogen ratios in other systems? Was 3I/Atlas a rare survivor, or is the galaxy full of similar relics that we have simply not caught yet? Authority matters here because the claims are large. NASA's own Comet facts page set the basic path and speed. Dr. Cynthia Phillips at JPL helped explain why Europa Clipper's ultraviolet view mattered. Cyrielle Opidum, Aravind Krishnakumar, Martin Cordiner, and other researchers tied the chemistry to a much older birthplace. The names matter because this story was not built from one headline. It was built from many careful hands. And the meaning keeps widening. If ancient low-metallicity systems could make icy bodies with familiar volatiles like water, but with different isotope patterns, then planet building may have been diverse much earlier than many people imagine. The young Milky Way may have been making cold archives long before our neighborhood existed. That does not prove life elsewhere, but it does enlarge the stage on which habitable chemistry might someday appear. It also changes how you, the viewer, can watch future space news. The next time you hear that an object is interstellar, do not stop at the passport stamp. Listen for the deeper words: ultraviolet, X-ray, isotope, deuterium, outgassing, trajectory. Those are the moments when a headline stops being a sighting and starts becoming a history lesson. And remember the quieter truth underneath all of this. 3I/Atlas never threatened Earth. The alarm was scientific, not personal. It was the kind of alarm that rings when nature answers an old question with more detail than expected. That kind of alarm is a gift. It tells us our instruments are getting good enough to be surprised in richer ways. What comes next will not look dramatic at first either. Somewhere, in data from a telescope or a spacecraft, another faint track will appear. It may look like dust. It may sound like a routine alert in the middle of the night. But after 3I/Atlas, scientists will know that a dim visitor can carry an entire lost chapter of galactic history inside a cloud of gas and ice. That is the forward edge of this story. Not the comet itself, because it is already leaving. The forward edge is the habit of attention it created. A wider net, a faster response, a more confident willingness to combine observations from many worlds and many instruments before the opportunity fades. In that sense, 3I/Atlas did more than pass through. It trained us. And the next horizon is even larger. If one interstellar comet can hint at a birthplace older than the Sun, then each future visitor becomes a time capsule with a return address we may partly decode. Not fully, not easily, but enough to begin mapping the diversity of ancient planetary systems across the Milky Way. We are not just spotting rocks anymore. We are learning to read exiles. Save this video and come back when the next interstellar object makes the news. That quiet habit will help you notice how fast the science changes while everyone else is still catching up. Because these stories do not end when the object fades from view. They keep unfolding in papers, in reanalysis, and in the sharpened questions left behind. So carry one image with you. A small comet, no closer than 270 million kilometers to Earth, racing near 250,000 kilometers per hour, glowing in X-rays after most people had already decided they understood it. Not loud, not huge, just unexpectedly legible. Like a single old key found in a drawer, heavy with a history the house around it does not remember. Or carry one date, July 1st, 2025. A routine report from Chile. A moving speck entered the record. Everything after that came from people refusing to let a faint object stay simple. That is one of the best habits science has ever built. My own guess is that this feeling will become familiar. Not panic, not certainty, something better. A steady readiness for the next quiet thing that arrives carrying a larger past than anyone expected. And when it does, we will be a little more prepared to listen.